Hello everyone. In this video and the next 5 videos, we will talk about chapter 5, which is the topic of confidence interval. And the main idea is the following. You have a population and you don't know what's the distribution, what's the probability density function if it's a continuous variable, or the probability mass function if it's a discrete variable. And you need to estimate what is mu, a parameter, or the proportion or the standard deviation of this population. This population could be a product manufactured by a factory like transistors, and the mean could be the lifetime for these transistors. Now, we want to estimate mu by a confidence interval with a specific confidence level. So I may say mu is 129 hours to 140 hours. And I am confident 98% that the actual value mu of this population will be in this confidence interval. And this is the topic of chapter 5. But there will be estimating the mean or the proportion or the variance and so forth. So the topics for chapter 5 will be the following. The first, finding the confidence interval of a population mean if we are able to take a large sample from the population. So I have the population here. I can take a large sample. That means n equal or larger than 30 to estimate mu of this population. The second topic will be confidence intervals for proportions. So now I want to estimate the proportion of success or the proportion of the products that meet specific criteria. The third topic will be confidence interval for a population mean, but I cannot take a large sample. I can take only a small sample because of some constraint that limit the samples I'm taking from the population. That means n is less than 30. The fourth topic is finding confidence intervals for the difference between two means. So now I have two populations, 1 and 2. And this is, let's say, mu1 and this is mu2. Now I want to find the confidence interval that estimate the difference. mu1 minus mu2, it will fall in this range with certain confidence level, like 98%. I am sure that will be the case. The fifth topic will be confidence interval for the difference between two proportions. Now I'm estimating the difference between proportion 1 here and proportion 2. The sixth topic will be confidence interval with paired data. Now here we have two populations, and I cannot just estimate the mean here and the mean here and find the difference like I did in this case. Why? Because this is paired data. That means I have to take one sample from here and one sample from here and compare both samples. Let's say I am comparing the mean. I want to know this sample coming from this population and these samples from this population, if they go through the same test. I exert the same stress on both of them and see how they perform. Then I take another sample from here and another sample. So that's the pairing. A scenario, maybe there is a certain machine or algorithm produce certain product here, another one certain product here, and I want to see how they compare, which one to buy. The last topic is confidence interval for the variance and standard deviation of a normal population. Now I'm trying to estimate the variance or the standard deviation of a population, but in this case I know it is a normal distribution. In the previous cases here, it doesn't matter if I know what kind of probability density function or not, because we will be using the central limit theorem to help us define the confidence intervals, regardless of the probability distribution of the population. Okay, so now estimating a parameter is not a new topic. We've seen it in chapter 4. We have a population here, but in chapter 4, we know what's the probability distribution of this population. It could be exponential or normal or uniform or binomial. So we know the distribution and we want to estimate the mean. We do a point estimate. That means we take a sample here and the number of items in this sample, n equal 30. So x1, x2, all the way to x30 or more. And then we find the mean by adding all these items in this sample and divide by n. And that's a point estimate. Is this estimate will give us the true value of mu? I bet you not. Because if somebody else take a simple sample of n equal 30, he will find here x different. A third person may find it different. So then we come up with a point estimate, and then we add the uncertainty, which is plus minus the standard deviation. If we know the standard deviation of the population, and if we don't know it, then the standard deviation here will be the standard deviation S of the sample mean divided by the square root of n. That's what we did in chapter 4. We have point estimate and we added the uncertainty. And we knew what is the probability distribution of the population. In this chapter, first, we don't know what is the probability distribution. It could be anything, but we will use the central limit theorem to estimate mu or p by an interval and with a certain confidence level. That's the idea. So section 1 basically is finding the confidence interval of a population mean if we can obtain a large sample. So the idea of this section is the following. I have a population here and I want to estimate the mean. The mean could be I'm manufacturing beams, and the mean is the strength of the beams under certain pressure. So we take a sample of size n equal or larger than 30. Then we find the sample mean, x. We know for sure if I take another sample here or a third sample here, the sample mean here, according to the central limit theorem, will have a normal distribution with mu x similar to mu of the population, and the standard deviation of the sample mean x will be the standard deviation of the population divided by the square root of n. If I don't have the standard deviation of the population, then I use the standard deviation of the sample, s over square root of n. And this random variable, which is the sample mean of different samples, will follow a normal distribution. That's the central limit theorem. And we will be using this central limit theorem. Now, the confidence interval of mu, I will say it is x, the sample mean, plus a is a constant that will be determined by the confidence level. Do I want to be confident that will be the case 95%? Time the standard deviation of the sample mean, sigma x prime. So this is the upper value. The lower value will be x prime minus a sigma x. And this is the confidence interval. If a here is 1, then the confidence level will be 68%. Because we said the sample mean, which is x prime, follow a normal distribution. And if standard deviation a is 1, then I am estimating the confidence interval to be from here to here. And the value of mu will be in this range with probability is this area, which is 0.68, which is 68%. Now, if I want a higher confidence level, then I have to increase a more than 1. Then the confidence interval will be larger, but the confidence level will be also larger. And this is the idea of this section. So let's go through examples and derivation to clarify this concept. So just to help you visualize what do we mean by the confidence interval and the confidence level, just imagine you have this population and it has mu that you don't know, and this population, like let's assume it follow a normal distribution, and this is the true mu that we don't know. So we took a sample here of size n, then we estimate mu by the sample mean, x bar. And then we specified plus minus certain standard deviation, maybe 1 standard deviation or 2 standard deviation. So I will call this like A, that's the standard deviation of x bar, which is the sample mean. And this A in this example here is 1.96. So then my confidence interval will be the sample mean of this sample. It may come here. Plus minus 1.96 sigma, that's plus, is here, and 1 x bar minus is here. So this is my sample interval. So I am 95% confident because this is mu, the actual value of mu minus 1.96, and this is mu plus 1.96. And this will be the area 95% confidence level. So for this sample, I might get this is x and this is the range, confidence interval. And the actual value of mu fall in this range. But there is a possibility where somebody took a sample here and calculated x bar, calculated sigma x bar, and found x bar to be extreme case here. And the confidence interval from here to here. In this case, out of luck, the actual value mu is outside the range, the confidence interval. Okay, let's learn the steps in determining the two-sided confidence interval to estimate the mean with a specified confidence level. So I have a population and I want to estimate mu. So the first step, we take a sample of size n, and in this sample we will have this data all the way to xn. And usually n will be 30 data point in the sample or larger. And we will estimate mu. When we say two-sided, that means if the probability distribution is normal and mu here, and I'm trying to estimate it, then I will come up with an interval x bar and a maximum value here and a minimum value here. That's what we mean by two-sided. So then I calculate x bar. Next step, I calculate the standard deviation of x bar. And how do we get that standard deviation? Two possibilities. One possibility, if I know the standard deviation of the population, then this will be sigma divided by the square root of n. If I don't know the standard deviation of the population, then I calculate the standard deviation of the data in the sample. And this will be s over square root of n. Now my confidence interval will depend on the confidence level. For example, if I say the confidence level is 90% or 95%, then I have to determine what z alpha over 2, and I will tell you what's alpha, sigma x bar. So I have to determine this interval and this interval, which will be the same. And this interval will depend on the confidence level. So to determine what is this z alpha over 2, I will go to the standard normal distribution with mu equal 0, and I will find what is z alpha over 2 here and z alpha over 2 here. This will be minus and this will be plus. If my confidence level is 90%, that means the area here will be 0.9. Then the area here will be 0.05, and this here will be 0.05. Because the area is 1 under the standard normal distribution. Confidence level 90%, that is 0.9 here. And 10% will be 5% on one side and 5% in the other side. And now I go to the table. I look what is this value gonna be for 0.05 probability. And after I look in the table the number, then z alpha over 2 will have plus minus. This is the plus, this is the minus. Now I use the z-score to find what will be mu, my estimate. It will equal x bar minus mu, the mean of the population that I don't know, divided by sigma x bar. And if I solve for mu, the unknown parameter, then I do the cross product, plus minus z alpha over 2 times sigma x bar equal x bar minus mu. So in this case, mu will equal x bar plus minus z alpha over 2 sigma x bar. And that is my confidence interval to estimate the population mean that I don't know And this symbol here, alpha, is the following. It's the area of this one here, we said, and the area of this one here. Alpha is 1 minus the confidence level. So that is 1 minus, in this example, the confidence level is 90%, so that's 0.9, so that's 0.1. And if I am using two-sided confidence interval, then it will be one side here, alpha over 2, one side here, alpha over 2. And that's how we come up with a confidence interval for a specified confidence level. Now here is very popular confidence interval for a specified confidence level. If I want to estimate a confidence interval with 68% confidence level, then I go one standard deviation. So Z alpha over 2 is 1. 90% confidence level, then Z alpha over 2 would be 1.645. 95%, 1.96, and so forth. So this Z alpha over 2 here, it could be 1 here, or 1.64, or 1.96, and so forth, depend on the confidence level. And just remember the following. Z alpha, when you look at the normal distribution, a confidence interval of 99%, that means the area here is 0.99. Then 0.01 will be distributed in these two little area. Okay, let's take this example. The sample mean for the fill weight of 100 box is 12.05 ounce. So we have a population that we fill boxes, and we take a sample of n 100 box, and the sample mean we calculate it to be 12.05 ounce. And the standard deviation S of the sample we calculated to be 0.1. Find an 85% confidence interval for the mean fill weight of the boxes. So mu will be x bar plus minus Z alpha over 2 times the variation in the sample mean, which will be S divided by the square root of n. Now my confidence level is 0.85. So alpha is 1 minus 0.85. So this is 0.15. So alpha over 2 is 0.075. So if I look at the standard normal distribution, I need to find this. Z alpha over 2, where this area is 0.075. And if I go to the normal distribution, 0.075 is closer to this value. So that will be here and here. So Z alpha over 2 is minus 1.44 equal minus 1.44. So the confidence interval mu will be x bar, which is 12.05, plus minus Z alpha over 2 is, instead of plus minus and here is minus, I will just put the number here, 1.44. Because this plus minus here will take into consideration this one and this one. This would be minus, this would be plus. Time S, the standard deviation is 0.1 divided by the square root of 100. So this is 12.05 plus minus 0.0144. Again, just to help visualize this confidence interval. See, if the confidence level 68% versus 95%, the confidence level will determine the Z alpha over 2. The larger the confidence level, that means this area will be large, this area will be small, so Z alpha as a magnitude will be larger than the 68% confidence level. So when Z alpha over 2 here become larger as the confidence level increase, the interval will become wider. And that's what you can see here. See 68% versus 95, 97. That line here is longer than this one, longer than this one. That line specify the confidence interval. So if I conduct the experiment 100 times, or I take a sample 100 times and estimate the mean with a confidence level equals 68%, these are the intervals I will be coming with. This is for each time I take a sample. If I conduct the experiment 100 times, 68 times, the confidence interval will cover the actual value of mu, like this case here. And there will be time where the confidence interval will be way off. It won't cover, like this one, and this one, and this one. Now, if I want confidence interval with confidence level 95%, then it will be wider. That's the disadvantage. Now I'm telling you mu is 12.05 plus minus a bigger number. So the interval will be larger, but 95% of the time, that interval will cover the actual value of mu I'm trying to estimate. And the same thing here, 99.7, almost all. The interval cover the mean I'm trying to estimate. So it depends on the application. If you really want to come up with a confidence interval that for most of the time will cover the actual value of mu for your design, and you can tolerate that a confidence interval will be wide, then increase the confidence level. If your application cannot tolerate a wider range, but it can tolerate few failure, then the confidence level can go down. So it depends on the application. You have to decide what's important. Let's look at this example. There is a sample of 50 micro drills. Okay, so we took a sample here and 50 of micro drills with an average lifetime expressed as the number of holes drilled before failure of 12.68. So X bar, the average lifetime, and standard deviation 6.83 divided by square root of 50. This is the standard deviation of the sample. Suppose an engineer reported a confidence interval of 11.09 to 14.27, but neglected to specify the confidence level. What's the level of this confidence interval? So they gave you X bar plus minus Z alpha over 2 S over square root of n, and they need the confidence level. So they gave us these, they gave us these, they gave us these, and we need to calculate Z alpha over 2. Well, X bar is 12.68, so that's here, and the upper bound in the confidence interval is 14.27, and the lower bound here is 11.09. So we need to calculate this. So this is X bar. So Z alpha over 2 S over square root of n equal this interval here, which will be 14.27 minus 12.68 equal 1.59. Now I need to calculate what is Z alpha over 2. So from here, Z alpha over 2 will be 1.59 times square root of n divided by S. So if we plug value, then I have here 1.59 square of 50 divided by 6.83. And this should give us 1.646. So I go to the standard normal distribution and I look where minus 1.646 here, 1.646 here, what is this area? And that area will be alpha over 2, and this is alpha over 2, and the confidence level that I'm after will be 1 minus alpha. So from the table I will find this quantity, and let's do that. Minus 1.6 is here, 46, that will be between these two numbers. So this is around alpha over 2. I can think of it as 0.05 because my Z here is minus 1.646. Okay, so we go back here. This equal 0.05. So then the confidence level will equal minus alpha will be twice that. 2 times 0.05, this is 0.9. So this confidence interval, the confidence level is 90%. So in this problem, we were given the confidence interval, but we are after the confidence level. So we calculated what is this z alpha over 2, and then we calculated what's alpha over 2, and then we found the confidence level. Now, when we estimate the mean with a confidence interval, x bar plus minus the interval. So x bar will be here, and this will be x bar plus z alpha over 2 sigma over square root of n. This is the interval. Now we always want that interval to be small. So the only way to make it small is to reduce our confidence level. But if I don't want to reduce the confidence level, then the only choice I have is to make n large. That means I take a larger sample, which makes sense because the more samples you have, the more information you have, and the better is your estimate interval. So let's take an example and look at this example. Back to the example of diameter of a piston using a sample of size 100. So we had a population, we took a size sample of N100. We found the confidence interval to be 14 plus minus 0.196 with confidence level equal 95%. Now we want to reduce the confidence interval to be 14 plus minus 0.1 instead of 0.196 and keep the confidence level the same. So z alpha over 2 sigma over square root of n, now I want it to be 0.1 instead of 0.196. And I want my confidence level to be the same. So for 95% confidence level, z alpha over 2 will equal 1.96. And here square root of n equal 0.1. And sigma, well, let's find the standard deviation first of the 100 piston. So we already have this information, z alpha over 2 standard and square root of 100 equal 0.196. And this is for confidence level 95%. So then sigma equal 0.196 times square root of 100 divided by z alpha over 2. For a confidence level 95%, z alpha over 2 is 1.96. So this will be 0.196 times 10 divided by 1.96. So that is 1. So now I can go back here and plug for sigma here 1 and solve for the square root of n. So in this case, square root of n equal 1.96 divided by 0.1, that is 19.6, and n will equal the square of 19.6, that is 384.16. So you round it always up, 385. So I need to take 385 sample to reduce the confidence interval from 0.196 to 0.1 with keeping the confidence level at 95%. Okay, now in some scenario, when you try to estimate a variable or the mean with a confidence interval, you don't need two sides for the confidence interval, low value and the high value. You care only what is the lowest value for the parameter you are trying to estimate. It could be, for example, you have a beam that you manufactured and you want to know how much pressure it can handle. So you don't care if it can handle high pressure, that's good. You are worried what's the lowest pressure it can handle. Then all you care is about a confidence interval that has a low, and you don't care about the upper value. And we call this one side confidence interval. Or sometimes it's the opposite. I'm creating electrical system and the input is voltage. I don't care about low input voltage. All I care is the high input voltage before it break the system. So I know if my system can handle it or not with a specific confidence level. And this we call it the upper confidence bound. So if I want the lower confidence bound, then that will be the estimate x bar minus, this is x bar minus z alpha sigma x. Now here we call alpha because if my confidence level is 95%, then alpha is 0.05, 1 minus 0.95. So then that will be this, because the 95% will be all these. And the remaining 0.05 will be this area. And that's why we call it Z alpha. Now, if I care about the upper bound, so I want to know what is the maximum voltage, then that will be X bar plus Z alpha sigma X bar. And this will be the 95% and this will be the 5%. And this will be the maximum value the input can have with a 95% confidence level. So let's look at this example. In a sample of 100 steel wires, the average breaking strength is 50 kilonewton. So I have a population that manufacture these steel wires. I took a sample, N is 100, and I found X bar to be 50 kilonewton and standard deviation of 2 kilonewton. Find 95% lower confidence bound. So I don't care if it can handle 60, 70, 80 kilonewton. That's good. That doesn't make me worry. I want to know what's the lowest it can handle. So that means I want to know what is this. And the confidence level, this is 95%. This will be 5%. So that is 0.05. And I have to use the table and look what is this value from the table such that this probability is 0.05. And if we do this, then you can find minus 1.645. So the lower confidence interval equal x prime minus z alpha sigma over square root of n. So this is 50 minus 1.645. Sigma is 2 divided by square root of 100. And this should come 49.671. So in this case, this is with 95% confidence level. The average breaking strength will be 49.671. Now the question here B, someone says that the mean strength is less than 49.8. With what level of confidence can this statement be made? So let's see first what is the confidence level for 49.8. So for this, Z alpha sigma square of n equal 50 minus 49.8. That is 0.2. So if this is 50 here, then this interval will be 0.2. And that interval determined by this quantity. So we need to solve for Z alpha to find what is the confidence level. So Z alpha sigma is 2, square of n is 100 equal 0.2, and from here Z alpha equal 1. And if I look in the table for the standard normal distribution and for Z equal minus 1 here, because I'm looking for the lower, this area here will be 0.1587. So alpha is 0.1587. So the confidence level will be 1 minus 0.1587. That is 0.84. So if somebody said the mean strength is less than 49.8, then the answer to this one will be 1 minus 0.8413. So this will be 0.15. So that is 15.87% confidence level. The mean strength of the steel wire is less than 49.8. All right, next section, we will talk about confidence intervals for proportion. Thank you and see you next video.